Hello friends. So today we are going to discuss a few questions which were asked in the year 2002. So there are a total of 3 questions from the year 2002. So the first question, it is asked that a particle of mass m and charge q moves with a constant velocity v along a positive x direction. It enters a region containing a uniform magnetic field B directed along the negative z direction, extending from x is equal to a to x equal to b. The minimum value of velocity v required the particle can just enter the region x greater than b is. In this case, we are given that, let us draw an approximate diagram for that. This is a x-axis and we have y-axis, and there are two coordinates given, x is equal to a and x is equal to b, and the magnetic field is only present between these two regions. And it says that a particle is traveling along x-axis with the velocity v, and we have magnetic field that is along the negative z-axis. So this is a magnetic field. So as soon as the particle enters the magnetic field at x equal to a, it will follow a, you can say, a semicircular path. Okay. And we want that it should just enter the region x greater than b. Okay, so we have to find out the velocity. Or in a simpler terms, we can say we have to find out velocity v such that the particle just touches this axis x equal to b. So as soon as the particle enter the magnetic field, it is going to experience a force. So you can say that when a charged particle enters a uniform magnetic field, the force acting on it, so we can write this as F is equal to Q V cross B, and this is the velocity is perpendicular to the magnetic field. So because of this, the resultant of the motion will be in a circular path. Okay. So let me write it here, that this force is perpendicular to both velocity and magnetic field. Thus, it results in circular motion. With radius r. R, and we can say the force is going to provide the necessary centripetal force. So based on this, we can write that our radius will be given as mv divided by q multiplied by b. So this will be the radius of the circular path. So we can say that somewhere, if we assume that center is somewhere here, we can say this will be our radius of the circular path. This is center. And we have to find out that the minimum speed v such that the particle just reaches x is equal to b. So basically, we can interpret this entire scenario with the help of a geometric condition. So we can say this is a geometric condition wherein the particle describes a circular arc and the maximum horizontal distance it can cover inside the field is the chord of the semicircle. Chord of semicircle that is equal to the diameter of the circular path. Equal to the diameter of circular path. Therefore, we can write that maximum horizontal reach is equal to 2r, and that will equal to b minus a. And radius we already know, so we substitute here, we get 2 into mv upon qb equal to b minus a. This gives us that velocity v will be equal to qb b minus a divided by 2m. So the options that are available to us, we can say the option number D, sorry, I think there is some mistake. Yeah, this won't be true. So the correct option is our here I made a mistake that the radius will be equal to b minus a, not 2r. So the option is, let me correct this one. So this is the velocity of the, and the option number B is the correct option. Option B is correct. And it should be radius, not a diameter. Radius of the circular path, not the diameter. Now we come to the next question, and it states that a long straight wire along the z-axis carries a current I in negative z direction. The magnetic field vector B at a point having a coordinate x, y on z equals 0 plane is. So in this case, we are given that we have a magnetic field, and that magnetic field is having a coordinate x, y, and we have to find out what will be the coordinate of that magnetic field. Yeah, so we can draw a rough approximate figure for that, and you can say that so this is a x-axis and we have a y-axis, and we are given that is a long straight wire along z-axis carrying a current I in the negative z direction at a point having a coordinate x, y. Okay, so let us suppose this is our coordinate x, y, and we have a conductor which is carrying a current in negative z-axis. Let us suppose the negative z-axis, and if we join this one, so we can call this as our R. So we can just draw the magnetic field will be perpendicular to this particular, so magnetic field will be in somewhere in this direction. So we are given that we have a infinitely long conductor, infinitely long current carrying conductor, current carrying conductor, and there is a point P. So this is a point P which is having a coordinate x, y. So let us call this as O. So this OP will be the position vector of this particular point. can say that the position vector OP makes an angle theta, and we can just draw a vertical line, and let's suppose this angle is our theta and this angle is also our theta. Therefore our magnetic field B at point P is perpendicular to OP, and we also know that magnetic field at any distance r is given as mu naught I upon 2 pi r. So you can write that magnetic field due to infinite wire is B is equal to mu naught I upon 2 pi r, and we can divide this magnetic field B into two components. One will be our along x-axis and another one will be along y-axis. Okay. You can say that the field can be resolved along x and y-axis. So we can say magnetic field along x-axis is our B sine of theta, and magnetic field along y-axis will be our B cos of theta. So this represent our I for our x-axis, and we have y unit vector for y-axis, but it will be in downward direction. So therefore, and moreover, we can write that P point has coordinates x, y. So let me draw this one here. So we have our P point coordinate x, y. So we are going to have our this will be over x and this will be over y, and we have angle theta which is like this, and this is our radius vector r. So based on this we can write that our sine of theta will be equal to y upon r, and we have cos of theta is equal to x upon r. So we substitute it in the magnetic field equation. We can say that our magnetic field B will be equal to, we have this as Bx plus By, which can be written as B sine of theta I minus b cos of theta j. We substitute value of sine theta and cos theta. We get this as b will be our common. We get this as y upon r I minus x upon r j. Now we substitute value of b. We get this as mu naught I upon 2 pi r, and this will be y upon r I minus x upon r j, which can be further simplified, is equal to mu naught I upon 2 pi r square y of I minus x of j, and our r square is nothing but x square plus y square. So you can say, but r square is equal to x square plus y square. Therefore, we get b is equal to mu naught I upon 2 pi x square plus y square y of I minus x of j. This is the magnetic field. Okay. So the option that's the correct one is our, we have here x of j and y of I minus x of j. I think A should be the correct one, y of I minus x of j. So the option number A is the correct one. Option A is correct. Now we have the last question from the year 2002, and it states that a rectangular loop PQRS made from a uniform wire has a length A, width B, mass M. It is free to rotate about the arm PQ, which remains hinged along a horizontal line taken as the y-axis. See figure. Take the vertical upward direction of the z-axis. A uniform magnetic field B 3I plus 4K B naught exists in the region. The loop is held in the xy plane and a current I is passed through it. The loop is now released and is found to stay in the horizontal position in equilibrium. So based on this entire description, we have three questions based on it. First of all, it is what is the direction of the current I in the PQ? Second, what is the magnetic force on the arm RS? And find the expression of I, that is current, in terms of magnetic field, side of this loop, and the mass M. So here, so we have figure. It is given that we have this PQRS and it is hinged at this arm Y, so that it is able to freely rotate about this axis. Okay. And the length is given as A and width is given as B, and it is released. It is said that this is in equilibrium. So on this entire loop there will be a force which will be acting downward, that will be mg, and it will be at a distance of a by 2, and upward force obviously will be because of the magnetic force, so that this entire loop is in equilibrium. So in the upward force we are going to have a force because of the magnetic field. If these forces balance each other, this entire loop will be in equilibrium. So important condition is there that the loop is in horizontal equilibrium. Loop is in horizontal equilibrium. And the coordinate of the magnetic field are also given to us, and the coordinate is given as B is equal to B naught 3I and 4K multiplied by B naught. So we can just draw approximate for it also. So we are given as a 3I. So 3I we can say will be somewhere along x-axis. So let us suppose this is our 3I, and then we have 4K. K will be all along our z-axis. So this is our 4K, and there will be a resultant of it which will be approximately somewhere like this, and this will be our magnetic field B. Okay, and this vector is our 3I plus 4K. And first of all, in the first part, we are supposed to find out the direction of the current, and the direction of current should be such that we have to find out direction of current in the PQ. Okay, only in the PQ we are going to find out. So the direction of current will be such that this entire loop remains in, you can say, equilibrium. So for the sake of convenience, let us suppose the current flows from P to Q and the value of current is given as I. So in the part A, we say that assume current flows from P to Q, and now we can find out the magnetic moment. So we can say that magnetic moment M is equal to I, and we have this as area and a unit vector. Okay, and it is said that the loop is in xy plane. So we are given the loop is in xy plane. Okay, therefore the area vector, which in this case is represented as n unit vector, is along minus k, and therefore we can write that our magnetic moment will be equal to minus I, and area will be length multiplied by breadth, and here we have k unit vector, and based on this we are going to find out the torque. So we can say torque on the loop, and that is our tau is equal to magnetic moment and our magnetic field. Magnetic moment we found out, and magnetic field is given to us. So we substitute both here, we get tau is equal to minus I AB k unit vector cross, and magnetic field is given to us as 3I plus 4j B naught. Now we can easily solve it. We get our torque is equal to minus 3 IAB minus 3 IAB, and we are B naught, and this will be giving a k unit vector, and here will be our I unit vector cross. sorry, here this is 4 and here it is k unit vector. Okay. So only thing, because k unit vector cross will be giving us a 0. So only thing left is our k unit vector cross I, and this will be equal to minus 3 IAB B naught, and here we have j unit vector. Okay. And let me write it here, that since our k cross k is equal to 0, now the torque due to gravity acts along the hinge of PQ. So we have two torques. Okay. So this torque is because of the magnetic field. So let us write tau B, and here is also tau B. Yeah, and here I mentioned that about the force, it should not be actually force, it should be the torque. My mistake. So we have the torque because of the magnetic field should be equal to torque because of the weight mg, which is acting in downward direction. Okay, my apologies for that. I said head force, it should be the torque. And next is the torque due to gravity acts about PQ, and it will be in downward direction. Therefore we can say that our weight, which will be our downward direction, acts downward, that is our minus k unit vector at the center of the mass, or we can say at the center of the midpoint, at the center, or we can say midpoint of the loop, and that will be at a distance, a by 2 from PQ, and its direction will be our so we can say that the position vector of, or we can say position vector from the hinge, to the center of mass, is a by 2 I unit vector, because it will be parallel to x-axis. Therefore we can write torque due to gravity, let us call this a tau gravity, is equal to radius cross product force due to gravity. We substitute the respective, we get tau due to gravity will be equal to, distance is a by 2 I unit cross force will be downward direction mg k unit vector, and we can write this as mga divided by 2, and here comes our j unit vector. Okay. So we have one torque acting in downward direction and the torque because of the gravity acting in the upward direction. Because of the minus sign, it will be upward direction, both in opposite side. So for equilibrium, net torque must be equal to 0. For equilibrium, net torque is equal to 0. Therefore, we can say torque due to magnetic field plus torque due to gravity is equal to 0. So this gives us that minus 3 I naught AB, sorry, is I naught, B naught, AB B naught J plus MGA divided by 2 J unit is equal to 0. Now it's a quite simple simplification. So this gives us 3 IAB naught is equal to MGA divided by 2. And here A cancel with A and rest remain same. So based on this, we can find out that the value of the current I will be equal to mg upon 6 B naught. So this is the magnitude of the current, but we are mainly interested in the direction of the current. Okay. And from the solution, we can clearly understand, because the direction we have taken is the correct one. So we can say, because if we take the direction of current reverse, that is from Q to P, both the torque will be acting in the same direction. Okay, so it will be in the downward direction. So that's why it won't be in equilibrium. So it means the direction of, or we can say the assumed direction, of current is correct. The current flows from P to Q. The current flows from P to Q. Now we are going to find out magnetic force on the arm RS. That is part B. Part B. And let me redraw the figure. We have to find out force on the arm RS. So the loop is something like this. So this is a P, Q and R, S. So direction of the current is our correct one, so it goes in this direction. And we have to find out the force on the arm RS. And we can easily say now the current I is flowing through it. So we can find out the force on the current carrying conductor in a magnetic field. You can say force on a current carrying conductor in a magnetic field, and that force is given as F is equal to I L cross B. And for arm RS, we can say the current flows from R to S. The current flows from R to S. Therefore, the length vector that is of L will be equal to minus B J unit vector, because B is in parallel with y-axis. Okay. So this is our y-axis, this is our x-axis, and here we have our z-axis. You can say RS is parallel to y-axis. Magnetic field we already know is given to us. B is equal to B naught 3I plus 4K. Now we substitute the value, then we get our force will be equal to, force on RS will be equal to I. Here we have minus of J cross 3I plus 4K, and here we have B naught. And we know that J cross I is minus K and J cross K is I. So we can write this as, this will be equal to I times B naught is equal to, we get this as minus 3B, we have a J cross I, and here will be our minus 4B, and here we have J cross K. Now J cross I, this is our minus K, J cross K is our I unit vector. Therefore, we can say force on RS will be equal to, we have an IB, not IB, but we have IB naught, and we can also take B as common, and this will be our 3K unit vector minus 4I unit vector. So this is the force on the arm RS. And finally, in the part C, find the expression of the current I in terms of B naught A and M. And we have already derived actually this relationship. Okay. So let us call this as equation number 1. So in part C, we can write from equation 1, the value of current was equal to mg divided by 6b times b naught. Mg is, yeah. So this complete this final question. Okay. And this question was asked in the year 2002. Thank you.